Okay, so welcome back, everybody. So hopefully the headset issues from yesterday won't happen now. I turned the auto turn off, so I won't have to I think it was set on like every 20 minutes if there's no sound. It cuts off, which was probably an annoying like 5 to 10 seconds of silence in the first lecture video. So anyway, also I saw like right after I closed stream yesterday, someone asked when will these be available. Recorded on YouTube immediately once it ends. So immediately once this ends, this will all be on YouTube. And anything I noticed that when I started this up, the title of it's still Lecture 1. Obviously, I'll change that to be Lecture 2 when I'm done today. So yeah, it's auto like you can even use the same link to access the video from Elms, the same link that I post in the Elms announcement. But also I make them public right after the stream ends, so you can they're available immediately after on the same YouTube channel. So and that'll be how all these are. So you'll always be able to immediately look at them. Okay, so where we ended yesterday was right after the proof of the second theorem, which said that in a graph G, if you have vertices u and v in G, every uv walk contains a uv path. So any walk considered in this way contains a path between having the same end vertices. So now I want to discuss a couple of operations on graphs that will allow us to talk about yet another way in which there's a connection between graph theory and topology, which is a notion of connectedness of graphs, connectivity of graphs. So a couple of operations. On graphs, which, as I said, will sort of illuminate what it is that's going on in terms of notions of connectivity. So we're going to talk about vertex deletion and edge deletion. Okay. And so these are mostly going to be the obvious things that you would think these are. Again, you know, the cool thing about graph theory is if you kind of imagine yourself coming up with these notions for the first time, like you'd never seen them or no one had ever told you about them, a lot of it is extremely intuitive in the sense that in almost every case, these are basically the things that you would have come up with if you were tasked with doing this. You'll be delighted to know that the same is true of a lot of the algorithms that we're going to discuss, especially the early ones, like Kruskal's algorithm. Uh, when we talk about like a lot of the algorithms and what they do on graphs, the nice thing about them is they are intuitive in the sense that they're basically what you would have come up with if you just thought about it for a little bit. So they're not typically some completely out of left field thing that you wonder, oh my god, how did anyone ever come up with this? No, they're usually the kind of obvious thing. So in this sense, the notion of vertex deletion. So what does it mean to remove a vertex from a graph? So given we'll talk about vertex deletion first. So given graph G and a vertex V that is in the vertex set of G, what is G minus V? So graph minus vertex. This is the graph obtained by removing the vertex and all edges incident with that vertex from G. It's a graph obtained from G by removing V and all edges incident with V from G. So I will do a couple of, actually, I'm going to show you all a couple of pictures here in a second that's going to illustrate not just this operation, but also edge deletion. So I'll save a picture for now, but you can already see where this is going. Of course, I am not just restricted to talk about removing a single vertex. What if I wanted to remove some subset of vertices from G all at once? So not just one, but several, right? 2, 3, 5, 10, however many. I want to remove a few of them. So imagine I have a set of vertices, right? So if S is a set of vertices, G minus S is the graph obtained by removing each vertex of S and all associated incident edges. So removing all vertices of S and all incident edges. Incident here meaning, of course, incident with these vertices that you've removed. Okay. So that is the notion of vertex deletion. What about edge deletion? So given G, and I'm going to use a single letter to denote the edge just to make it easier so that I don't have every single edge denoted by 2 letters here. So let's say that E is an edge. So E is an edge in the edge set of G. What is G minus E? G minus E is the graph obtained from G by removing that edge, and that's it, and nothing else. So I will emphasize here, i.e. the end vertices remain. So only the edge gets deleted. Its end vertices do not also get deleted. Okay. In the same way, if T is a set of edges, then G minus T is the graph obtained by removing all of those edges, and all the end vertices will remain. So G minus T is the graph obtained by removing each of those edges. Oh, going a little bit off the page. Okay, so what are examples of this? So here's a nice picture that I will show you. Let me make sure. I might need to refocus here. Hold on. Okay, here we go. So consider the graph G here. All right, so there's our graph G. We got our vertices nice and labeled. Okay, so G minus the vertex D is this. And think for a second why this is. We didn't keep all of the labels here because it would be kind of annoying. But why is this G minus D? Well, if I remove D, I have to remove that vertex and any edge incident with it, right? That makes sense. So this edge is deleted, this edge is deleted, this edge is deleted, and this edge is deleted, right? So 4 edges and D are deleted, resulting in this. All that's left behind is exactly this. Okay. Let's look at another vertex deletion, or a vertex deletion rather of 2 vertices, F and G. So G minus F and G. So we're removing F and G and any edges incident with F and G. So F and G are gone. So of course this edge is gone, but also these other edges connecting D to F and E to G are also removed, and so all that is left is this. Okay. Similarly, here, this is G minus the edge CD. So notice it is almost the same as G. The only difference is the single edge has been removed. Right? And similarly, G minus EGFG, I'm only removing these two edges, EGFG. There we go. Okay, so pretty intuitive operations here. You might already be thinking about how this relates to a notion of graph being connected, but we haven't actually even defined what it means for a graph to be connected yet, right? So what does that mean? So I'll just put it here. A graph G is connected if any two of its vertices can be joined by a path. Now, you might say, wait, wouldn't it be sufficient to say that any two of its vertices could be joined by a walk? But pick any two vertices. If there is a walk between them, there is a path between them by the second theorem. So this definition works completely fine, right? This is fine. If depending on your math background, you may immediately notice that, of course, here our notion of path has a very specific meaning. Your notion of path may differ slightly. It may be it may have to do with continuity, for instance, if you're talking about this topologically. But the point is that you notice, hey, this is just path connectedness, right? This is literally the notion of being path connected in a more in a topological setting. Here, there is no difference between connected and path connected. Those are the same thing. That is how we're defining connected. So we will only talk about being connected in this context. Of course, what is a way to think about this kind of informally? The intuitive way of thinking of a connected graph, of course, is can I take the graph and pick it up by any of its vertices? Now, if I lift it off the page, does it lift in its entirety, or is some stuff left behind? Right? That's the intuitive idea. So, for instance, we'll look at this graph, right, from yesterday. Is this graph connected? Yes, because any vertex that I pick here, if I lift it up off the page, all of this gets lifted with it. Right? Of course, you could also say pick any two vertices, there's a path between them. You could find that path if you needed to, but this gives an intuitive way of thinking about this versus, say, this thing, right? So this thing, this is not connected because if I grab this vertex, only this part lifts. I still have another part of the graph left. Of course, this thing is also not connected because if I pick this vertex or any of these vertices up here, everything goes except this vertex is left behind, so not connected. Again, you could also just say, hey, there's not a path between, say, this vertex and that one, right? And that's enough to say that it's not connected. Okay. So, if a graph is not connected, then some parts of that graph are disconnected. But the notion of connectedness forms an equivalence relation. You can talk about being connected. This partitions your graph, if you like, into maximal connected components. Okay, and so we might notice that, again, let me bring back this example here. So this thing, while this graph, G minus D, is not connected, because it has a piece here and a piece here, each of these pieces is connected. So this piece is connected, this piece is connected. So it is separated into two connected pieces. These maximal connected pieces of the graph are referred to as its connected components. So any graph can be split into some number of its connected components. These are the maximal connected pieces of the graph. Okay, and so while the graph as a whole might not be connected, you could discuss working in a connected component of the graph. You might imagine immediately this is like how you might deal with a proof involving a disconnected graph. If you want to claim something that requires connectivity, you might not be, if the graph is disconnected, you're not going to be able to say it for the whole graph, but maybe you work in a connected component and you say, okay, well, now I'm in a part of the graph that is itself connected. I can maybe consider this as a subgraph or something. We'll talk about that in a little bit. We'll talk about the notion of a subgraph. But anyway, these pieces, these maximal connected pieces, are referred to as a connected component. So I'm going to put it here, and then we'll move on. So these are the largest parts of the graph that are connected themselves. Okay. And so if we want to see some examples, again, I'm going to use the pictures here that are in the book for us. So you have 3 examples here. Okay. We have a connected graph. This is a disconnected graph. This is another disconnected graph, but I want you to consider this disconnected graph for a second, because when you look at something like this, right, you're doing intro graph theory stuff, your brain has an idea, just like it does here and here. These intersection points, your brain can try to trick you into thinking that somehow these are included in the vertex set. They're not, right? The vertices are very clearly indicated here. These intersections don't matter at all. That's not tracked really by the graph at all. That's just for us, right? That's for our sake of drawing a picture the way we want to. We don't have to draw it like this. We could have drawn it, in fact, as 2 disconnected triangles, right? That is, in fact, what is going on here, right? So if I'm looking at how many connected components these graphs have, this has 1 because it is in fact connected, so it has a single connected component, the graph itself. This has 3 connected components. There's this piece, and that piece, that single vertex. Those are 3 connected components. This graph has 2 connected components. There's this component, the upside down triangle, and the other component, the right side up triangle. If I had just redrawn this as the following, so if I had redrawn this as I'm off camera. The question is this graph, maybe I call this G4, is this graph the same as this one? Well, that's a little tricky, because what does it mean to be the same graph, right? We are going to talk about that today here in a little bit. But This is a little bit of a tricky notion. As it turns out, yes, this is the same as that other graph that I just showed you. And here you can very clearly see the two connected components, while in the other graph maybe you first looking at it you're like, I don't know, I can't see. But that's what's going on. Okay, so that's the notion of connected component. So if the deletion of a vertex from G causes the number of components to increase, that is referred to as a cut vertex. So here, if the deletion of V from G causes the number of components, connected components of G to increase, we say that V is a cut vertex of G. Okay, going back to my picture here, D is a cut vertex of the graph G because when I delete D, now the graph has two connected components. Where it was a connected graph before, so it had one connected component, now it has two, so D is a cut vertex of the graph G. Okay. What about F? Is F a cut vertex? No, because getting rid of F doesn't increase the number of connected components. In fact, getting rid of both F and G doesn't increase the number of connected components. G minus F and G is still a connected graph, right? So neither F nor G are cut vertices, but D is. All right, removing D itself increases the number of connected components. Removing both F, G, you could even remove F, G, and E if you wanted to. You'd still have a one component thing. So D is a cut vertex, but F and G are not, for instance. Okay. All right. So we say that E, an edge, is a bridge if the graph G minus E has more components than G. So let's go back to this picture. Do you see a bridge in this graph? I'll let you think about that for a second. Is there an edge you could remove from this graph that increases the number of components? Can't remove FG, that doesn't increase the number of components. DF doesn't increase the number of components. EG doesn't either. DE doesn't increase the number of components. CD, nope. AD, nope. AC, nope. What about AB? Removing the edge AB leaves B on its own and everything else connected. So the only bridge in this graph is AB. If you delete the edge AB, you have caused the graph to now have two connected components instead of just one. Okay, removing no other edge does that. So AB is the only bridge in this graph. So all this is an example of this terminology. It's going to help us talk about the notion of connectivity. So now, if we extend this notion of cut vertex to a set of vertices, or try to extend this notion, to now a set of vertices or what we're going to call a vertex cut set. What is that going to mean? So a proper subset S of vertices of G, I could have just written a subset S of V of G, is called a vertex cut set. Sometimes it's just called a cut set. If the graph G minus S is disconnected. Okay. So remember, disconnected just means not connected, right? So just maybe to remind you, this means not connected. So that's all it means. It does not mean totally disconnected. When you think of disconnected, it doesn't mean it's just a bunch of vertices without any edges. No, it just means that it is not connected. Okay. What about like the opposite of a graph that is either not connected or is somehow barely connected? Now, obviously, something's either connected or it's not. That's how we've set up the definition. But you might already be thinking, because we've been talking about these cut vertices, there are going to be some graphs where removing a vertex makes them very disconnected or just disconnected, right? So we already saw G, if you remove D, now it is disconnected. Okay. So while G is connected, it's fully connected, we're happy with that. There exists a single vertex that if you remove that, it becomes disconnected. Well, what if I had a graph that was so connected that removing a single vertex like that is not going to, like, basically there is no cut vertex for the thing, right? So it doesn't matter. Any single vertex I remove is not going to make it disconnected. Like, what would that graph look like? And you might imagine to yourself, oh, well, just imagine a graph that has the most adjacency, right? It's every single vertex is adjacent to every single other vertex. What would you call a graph like that? We call it a complete graph. So a graph is complete if every vertex is adjacent to every other vertex. Well, okay. I mean, that's, you can already think what that would look like. This may be similar to like drawings you made in grade school when you were doodling and connecting dots on your own. You may have come up with something that looks like this or is this sort of thing. We're going to see this as we move into the section on special types of graphs that we're going to have special names for. We're going to talk about all these, but this is our first instance of mentioning this. So, of course, if a graph contains at least one non-adjacent pair of vertices, that graph's not going to be complete. So being complete is a very simple relation for the vertices to have. They're all adjacent, right? So it's very easy in a way to see if a graph is complete or not. Notice that complete graphs have no cut sets. It doesn't matter how many vertices you remove, it's always going to be connected. So note, complete graphs have no cut sets. G minus S is always connected. Well, that's a natural consequence of having the, quote, most connectivity, right? But in a way, this, while, right, like our notion of connectivity is something's either connected or not. It's either connected or disconnected, okay? But this notion of being more connected is not entirely silly, and in fact, we can actually rigorously track this with the next concept that we're going to talk about. So the other thing to say, but every non-complete graph, that is any graph that has at least two vertices that are not adjacent to one another, every non-complete graph has some cut set. It makes sense then to talk about the size of this cut set, right? That is, thinking about how large this cut set is. This is going to lead us to the notion of the connectivity of G. So maybe I'll give myself more room here so I can write more things. So for a non-complete graph G, the connectivity of G, which we will refer to as kappa of G, is the minimum size of a cut set of G. And when we say size here, we're not talking about graph theory size, we're talking about cardinality. I use the naughty word size to talk about a set. I should have said cardinality, but it's fine. This is the minimum size of a cut set of G. Okay. So naturally there are some bounds here. So if G is a connected non-complete graph of order n, so it has n vertices, then naturally the connectivity has to be between 1 and n minus 2. If G is disconnected, we don't need to remove a single vertex for it to already be disconnected because it is already disconnected. So we say that the connectivity is 0. Minimum size of a cut set is 0. I don't need to take away anything from the graph for it to be disconnected. If G is complete of order n, then we say that its connectivity is n minus 1. This will make the things we want to say about connectivity match, work out. Okay. This connectivity allows us to say, it allows us basically this notion we were kind of being silly and talking about something being more connected than another thing, but it turns out we can actually use this to say exactly that sort of thing. So we say G is K connected if the connectivity of G is at least k. Of course, saying what the connectivity is, it means that the minimum size of a cut set of G is at least k. Right? It can't be smaller than k. So notice by the previous assertion, one connected just means connected. So if you're one connected, you're already doing good. You're already connected. Okay. Having that k be higher means you are more connected, right? Like I said, there very much are notions in which we are going to be interested not simply in the graph being connected, but it being maybe more connected than just generically connected. Okay. So here are some facts. Some of these will be homework. Your first homework will be posted after tomorrow's lecture, and it'll be due on Monday at we'll say 11:59 p.m. Just to give you all day Monday in case you look at it over the weekend, you have questions you want to ask in chat on Monday before lecture or during lecture or whatever. You can do that. So yeah, I'll assign your first homework tomorrow. We'll say tomorrow afternoon, tomorrow after lecture. So some facts about this. One, a graph is connected if and only if its connectivity is at least 1. Okay, this is mostly just unpacking definitions here. 2, connectivity is greater than or equal to 2 if and only if G is connected and has no cut vertices. So the connectivity of G is greater than or equal to if and only if. To abbreviate if and only if, I'm going to use this, which you have likely seen before. If not, there it is. I may also sometimes use the double-headed arrow, right, to show that the implication goes both ways. If and only if statement, as you know, if you're proving an if and only if statement, you actually got to prove two statements. You got to prove the forward and backward direction, right, that this implication goes in both directions. So rest of the course, I'm going to use either this or this. But the connectivity of G is greater than or equal to 2 if and only if G is connected and has no cut vertices. Again, this is mostly just unpacking the definitions here. 3, every 2 connected graph contains at least one cycle. Interesting. I remember our definition of cycles from yesterday. And lastly, for every graph G, the connectivity of G is less than or equal to the minimum degree of G. So again, recall our definition of minimum degree from yesterday's lecture. Okay. So that's that. Okay. So our brief discussion of connectivity for now. Now you'll notice that obviously we had this in talking about connectivity, we naturally thought of an example that was like the most connected thing we could think of, right? That also might turn you on to the opposite of that, which is the most disconnected graph you can think of. Um, this way of developing your intuition by trying to break the statements involved is one of the best possible ways to like build your intuition, not just in graph theory. This is in math, right? Like if you tell me to draw a triangle, right? If you tell me to draw a triangle, or if I had you, I gave you the pen and asked you to draw a triangle, maybe you would draw a triangle that looked like this. You might draw, like I did a bad job here. If I was trying to draw an equilateral triangle, maybe you would draw an equilateral triangle. Maybe you would draw a right triangle because you like the Pythagorean theorem. Right? You would draw a right triangle. You draw something like this. Maybe. But what you probably wouldn't draw is something like this. Right? Maybe you would. Maybe this is how you think of it too. But the reason why, if someone asked me to draw a triangle, I wouldn't draw this or this, but I would almost always draw something like this, is not because I'm being mean to them and trying to, subvert what they were expecting me to draw. It is that all you said was triangle, right? And if all you say is triangle, then I'm going to draw like the thing that kind of embodies the most generic triangle, which is that it can be something like this. Let's say this is isosceles. This is a special type of triangle. If I drew an equilateral triangle, that's a very special kind of triangle. This is a right triangle. It's also a special kind of triangle. This is a generic triangle, and in a sense, most triangles look like this. If you don't tell me anything else about the triangle, this is what I'm doing. So I'm trying to basically draw the thing that is the most generic in some way, and I'm failing to do that if this is what I'm thinking of, right? So if I'm trying to make a statement about all triangles, this is much more representative than any of these. So in the same way, right, it's natural to, when I give you a graph and I say, a connected graph, of course, a generic connected graph is not going to be maximally connected. A generic disconnected graph might have a single vertex that's off on its own. And everything else, it might be like complete except for a single vertex, right? So the idea is not to, focus on the special graphs as representative of graphs, but nevertheless, now I'm going to say something that seems almost at odds with what I just was saying. These special triangles are extremely important, right? In fact, to our understanding of things, these triangles are more important than this generic triangle in a way. Because the special things allow us to do things with them we couldn't otherwise do for a generic triangle. And that's good, right? So that's good. And of course, it turns out that even though these are special, they still come up in very, very many applications or areas where I would want to talk about triangles. So just because they're special doesn't mean they're extremely rare or anything. So it makes sense to talk about special types of graphs. But the thing that we should kind of use to, as our best way of coming up with these special kind of graphs or thinking of them intuitively is, well, we're just naturally led to them by what, what we're considering. So like connectivity, for instance. A complete graph is like a maximally connected graph. It makes sense to start there. Then we can think of, what about a graph that is maximally disconnected? Well, we'll do that next. So, special graphs. Special types of graph. These are special enough that they have names. So, 1, complete graphs. So complete graphs of order n, we will denote this as k sub n. So k sub n is a complete graph of order n. So here's an example. All this talk about triangles. Might as well draw this one, of course. Doesn't actually matter what this triangle looks like. This is k sub 3. This is a complete graph of order 3. So it's complete. All vertices are adjacent to every other vertex. There's only 3 of them, so that's what it looks like. You might say, wait, you skipped one. How about this one? It's a complete graph of order 2. Now, there are a number of ways you could draw these. Again, I don't have to use any equilateral triangle here. I could use whatever triangle I want. This, of course, I could stretch this line however I want to. It's not important. What about k sub 5? So if I want to make it look nice, maybe I have the vertices be the vertices of like a regular pentagon, but of course I don't need to do this. Okay, so each vertex needs to be connected to every other vertex. So I know, for instance, this is how we do it. Hold on, let me make these vertices bigger so that it's clear where my vertices are. But now this needs to be connected to all the others too. So it needs to be connected to that vertex. It needs to also be connected to this vertex. Similarly. What are we missing? Oh, there we go. We got it. All right. This is the complete graph of order 5. Okay. So you can keep going as you like. You can draw these any way you want to that's visually pleasing to you, so long as it's clear that every vertex is adjacent to every other vertex. Now, this was our example of a like maximally connected graph, right? So now, what about a maximally disconnected graph? This was our other extreme. This is known as an empty graph. What about an empty graph of order n? So empty graph on n vertices. We'll label that as E sub n. Here's the empty graph on 4 vertices. Again, this doesn't need to be a square, but you get it. Here. Okay. Nothing much to say there. What's an empty graph? It's a graph that has no edges, right? So the edge set is empty. If the vertex set's empty, there's no graph, right? But if the vertex set's not empty, vertex, you have n vertices, so it's just some finite set, but the edge set is empty, you get an empty graph. So here it is. Obviously, this is like the other extreme, right? So if these are maximally connected, this is like maximally disconnected. Okay, it has like the most connected components possible. Okay, now is a good time to go ahead and discuss the notion of graph complements. So I'll call this you could think of it about this as a type of operation on graph, but it's vertex and edge deletion, you kind of think of happening one object at a time, right? One edge or one vertex at a time. Even when you're talking about sets, you're still basically doing it one at a time. This is, well, maybe you'll see that you might find this a little different. The notion of complement. So what is the complement of a graph G? So given G, G bar, its complement is the graph that has the same vertices as G, but exactly the opposite edges, meaning the only edges in G bar are the edges not in G. Okay, its complement is the graph whose vertices are the same as G, but whose edge set consists of all the edges that are not in G. So here's a really good example from the textbook that you can ponder. So on the left is G, on the right is G bar. Notice the vertices are exactly the same, so G has these 6 vertices, G bar has the same 6 vertices, but G bar's edges are exactly the edges not present in G. So this one's in G, so it's not in G bar. But this one is not in G, so it is in G bar, and so on. You see how looking at these, it might not be immediately obvious that one is a complement of another, especially if they weren't drawn in such a suggestive way. So if I took these vertices and I changed how they were arranged, I didn't put them in a hexagon anymore, I just kind of had them off, you'd see how it'd be really hard, potentially, to see how these things are related. And that's just something that we're going to have to deal with. We'll think about these things soon. So very soon we're coming up with the notion of whether graphs are the same or not. Okay. Okay. Now, what about something that you might think of as similar to complete, but it's a little different? Okay, the notion of a regular graph. What is a regular graph? A graph is regular if every vertex has the same degree. So G is regular if every vertex has the same degree. Say the degree of some vertex V in G is R. Then this R is the degree via which G is regular, so every vertex has that degree, so we say G is regular of degree R. Okay. Notice we have already seen 2 examples of regular graphs. Right? Complete graphs are regular. Of degree what? Well, they're connected to every other vertex. If there's n total vertices, there's n minus one other vertices for any vertex, so they're regular of degree n minus one. Empty graphs are also regular of degree 0, right? None of the vertices are connected to any other vertex, so this is like the complete opposite of this. Okay. All right. What about some other regular graphs? So here, I'm not going to go through why these are regular, but we'll check here in a second. Let's look at this example. Oh, hold on. Freaking out. There we go. These two graphs are regular. In the first graph, if you're believing the person that told you this, the second you know they're regular, you only have to look at a single vertex to see what the degree is. So on the left, the degree is 3, right? And then you can verify that every single vertex has degree 3. On the right, what is the degree? 1, 2, 3, 4. Right? So every vertex has degree 4. And you can just check that that is indeed the case. Okay. All right, what next? We have cycles. Now, we know what a cycle is in a graph, but what if we took any particular cycle in some graph, say it's a very large graph, we took a cycle of some size and just considered that as a graph itself. Right? What would be an easy way to represent that? C sub n is a cycle on n vertices. Well, this is easy enough to represent. 1, 2, 3, 4, 5, 6, 7. To draw a cycle on 7 vertices. Just connect each vertex to the next one. All right. Okay. You might say, wow, that's a really simple graph. Surely, you know, if this is what I'm dealing with and I'm asked questions about it, I'm very happy. These are still very important examples because when you see a statement, right, like the point of these special examples that have names is when you see a statement about graphs, if you have to think to yourself, okay, does this apply to all graphs? If so, it has to apply to all these special types. So then you run through in your head and you kind of check that it is verified for all those types that you know. If the statement that you're considering isn't true for all graphs, it's true for graphs having a certain property, you could check with the mental like inventory of these examples and see, oh, does this match up, right? Which of these graphs satisfy this, and then it has to apply to those special types of graphs. So that's kind of the idea of having this. You're building up an arsenal of examples that you can mentally check whenever you see some statement or an assertion being made about graphs or a type of graph. Okay, so paths are another of this sort. So what is a path on n vertices? We'll call it P sub n here. This is, let's do like P sub 5. Right. You don't have to have it drawn like this. Of course, you could have it drawn however you want, but this drawing it as a line like this or a bunch of line segments, perfectly fine. Now we're going to get into this is always the part in mathematical structure studying where things start to get in some fields, right, considering sub-objects is maybe not as big of a deal, but I'm going to say that in almost, I'd have to think hard to think of an example where, well, I guess sets versus subsets maybe is an example where there's almost no structure. But groups versus subgroups, manifolds versus submanifolds, that's a really tricky one. There's passing to the sub object is always a very interesting thing that kind of illuminates what's going on in the field typically, and we're going to talk about this in a couple ways here. So what am I rambling on about? Subgraphs. When you have a graph that arises as part of another graph. Okay, so the notion of a subgraph is pretty intuitive and pretty simple. This is just it is a graph whose vertices and edge sets are just subsets of the vertices and edge sets of the other graph. So stop rambling and write this out. So a graph H is a subgraph of G if the vertex set of H is a subset of the vertex set of G and the edge set is a subset of the edge set of G. Okay. In this case, we say H is a subgraph of G. That's what that symbol means. And we say that G contains H. Okay. Now, here's a tricky bit. In a lot of the examples that we've been drawing, right, like I didn't actually label the vertices, right? So going back here, even for my complete empty graphs, I didn't actually label the vertices here. I left them unlabeled. So here's something. How can I say that one graph is a subgraph of another if I haven't even labeled the vertices, right? Well, me not labeling the vertices, you could view that as a visual thing. Those vertices exist in a set. They have some labeling applied to them. Whether I've used numbers, letters, whatever I've used, that's fine. The idea is if I could label these things in a way in which this is the case, then we say it's a subgraph. So that's a little technical thing we have to say. So in a graph, maybe it's best to just write it out and not leave it as a single sentence that you might gloss over when you're looking at this video later. So in a graph where the vertices and edges are unlabeled, we say that H is a subgraph of G if the vertices could be labeled. In a way such that the vertex set of H is a subset of the vertex set of G and the edge set the edge set of H is a subset of the edge set of G. Okay, so here's a quick example. And you're I want you to ponder this because you're quickly going to see that this might take a little bit of thinking because there's not a standard way to present graphs, right? Like you might come across a graph and it's up to you to organize how it looks in a way that is comprehensible to you. So here are 3 graphs, or 4 graphs even. So here's the graph G, and here's the question. Which of these, maybe you already saw it answered down here below, but which of these H's is a subgraph of G? Well, turns out that H1 is a subgraph. H2 is also a subgraph. See if you can find that one. H3 is not. So, I'll just repeat that. H1 is a subgraph of G. H2 is also a subgraph of G. H3 is not. Before figuring out why H1 and H2 both are subgraphs, why is H3 not a subgraph? Can you see why? First of all, what do you notice about the degrees here of all these things? You notice that H3, every single vertex here has degree 4. Right? There are some degree 4 vertices in G. Right? But just look at how many edges you have in G versus H3. Right? Okay. H1, you might be able to actually see where it is, right? It's this and then, say, that one. Or this and that one, however you want to say it. H2 might be a little trickier, but see if you can see exactly how to match the vertices up in a way that this is indeed a subgraph of G. Remember, you're allowed to not have, like G has edges that don't have to show up here, right? G has vertices that don't have to show up here. This is a subset of the vertices, so you're picking 4 vertices from G and some of the edges of G, right? So that is the notion of a subgraph, and I want you to ponder that. If you didn't understand that example, have a look at it and understand it before moving on. There's very little rules here for how this H is a subgraph of G, right? You could literally, for instance, you could take the empty graph. So given a graph of order n, you could take the empty graph on n vertices. That's going to be a subgraph of it. You might say, but wait, it has no edges. Well, its edge set is the empty set, and the empty set is a subset of every set. So there you go, right? It's all that is easily satisfied. All the requirements for being a subgraph are satisfied. The next related thing is the notion of an induced subgraph. So this is important because there are going to be things we talk about later down the road that are going to rely on us understanding an induced subgraph perfectly because there are going to be statements that we make that have to do with what are called forbidden subgraphs. Okay, there's statements we want to make about graphs being nice based on the fact that they do not have certain induced subgraphs. And it's important that you use induced here because using subgraphs, period, would be no good. That would include too many things. So using induced subgraphs is going to be the thing that allows us to talk about the concept of having a forbidden subgraph. There's a graph we'll talk about soon called the claw, and there are facts about certain graphs that you get if your graph is claw-free. And being claw-free means it does not contain the clause and induced subgraph. So when we get there, we'll worry about that stuff. But it's good to just go ahead and get the intuition out of the way right now, so that we're not, we're not saying we're not having to like go back and think about this later. So this is going to help your intuition for other things anyway. So what is an induced subgraph? So given a graph G and a subset S of its vertex set, the subgraph of G induced by S which we will denote using these corner brackets around S, is the subgraph of G whose vertex set is S, with edge set that is the collection of all edges between vertices U and V such that U and V are both in S, and this edge is also an edge of G. So we're not making any connections that didn't exist, but we're only taking the edges both of whose end vertices are in S. i.e., writing that out in words instead of just set builder notation, what does the induced subgraph S look like? It contains all vertices of S and all edges of G whose end vertices are both in S. This is very important. Okay. It's very important because this is a lot hinges on the particulars here. A lot of statements, if you don't nail down your understanding of induced subgraph, a lot of the statements that we want to make about induced subgraphs are just false if we use subgraphs instead. Okay, so that's the main thing. I'll talk about this a little bit more when I'm giving counterexamples of certain statements or examples of certain things, because you might look at some of these things and say, wait, I see something. I see a naughty subgraph that thing has, and we'll discuss why it's important that it does not have it as an induced subgraph. So let's see an example of this real quick. So on the left is a graph. I've labeled the vertices, or well, I have not labeled them. The textbook has labeled them. So the vertices are labeled here in this graph. Here are two examples of induced subgraphs. You can see exactly what has been done here. So what vertex set did I choose in this case? Well, I chose the vertex set BGCD. BGCD, there's the vertices over here in this graph. So here's BGCD. Notice that I took B, G, C, and D, so those four vertices, and then I took only the edges, both of whose end vertices are one of these four. So for B, I took the edge that goes to G and C because those are both in this set. I did not take the edge that goes to F or A because F or A are not in this set that I've chosen. So the only edges that I took are from B are going to G and C because they are also in the set. Similarly, at G, I only took the edges going to B and C because they're both in the set. I did not take any of these other edges, right, that have G as an in vertex. For C, I took 3 edges. I did not take the edge with E because E is not in this set, but I took all the others. D, I only took the edge connecting it to C. I didn't take the one connecting it to D for the same reason. And you should go through and verify that this graph here is also another induced subgraph where the set S of vertices that I chose was G, F, C, and E instead. Right? Okay. Again, we're going to be returning to that a lot because understanding an induced subgraph is important here because we are going to use this to talk about, like I said, the notion of a forbidden subgraph. Okay. Okay. Continuing on with our idea of special types of graphs. Bipartite graphs. One of our most important examples of a graph that frequently gets forbidden in some statements is the claw, which is a bipartite graph. So more generally, what is a bipartite graph? It's a graph that has 2 parts, but we don't mean that in the connected component sense. Okay, so it means that its vertex set can be partitioned into 2 sets x and y so that every edge has only one end vertex in one or the other. And that sounds like a lot. Let's write it down. So a graph G is bipartite if its vertex set can be partitioned into 2 sets, we'll say x and y, such that each edge of G has one end vertex in x and the other in y. I should say one end vertex here. X and Y are called the partite sets. There's 2 of them, hence bipartite. Okay, X and Y are the partite sets. So what are some examples? There. There's one. Well, here is what I'll call my X set. It contains that vertex alone. And here is my Y set. Obviously, this thing that I'm doing is not part of the graph. It's just me illustrating which vertices are part of which thing. So here, this vertex is in the X set. This vertex is in the Y set. Every vertex here, there's only one of them, right, is connected to, each edge in G is connected on one end to this single vertex in X, the other end to some vertex in Y. Okay. So let's do another one. Here, let's take this example and maybe just increase the number of vertices here. So as in here and here and here and here. Right, something like that. Again, I have 3 vertices here, 4 vertices here. I can view this as being a set called X, this as being a set of vertices called Y. Every edge present in this graph has one end in X and the other end in Y. How about this? Is that graph bipartite or not? So I'll give you a few seconds to think about it. Is this bipartite or not? What do you think? You can say so in chat. I'll give you like another 5 seconds to say whether or not this is bipartite. It is, but notice what you can't do. You might be tempted, of course, because I've done it in these other 2 examples, to say, well, here's the X set and here's the Y set, but why is that not going to work? Well, you can't do that because if you circle this, right, these 2 edges have an edge between them. Or sorry, these 2 vertices have an edge between them. Okay, so these 2 vertices have an edge between them. They can't be in the same partite set because then not every edge of G would have one end in one of the sets and one end in the other set. So if you made this your X set, that's no good. Similarly, if you made this your X or Y set, that's no good either. So how is this bipartite? Well, those 2 are in X and those 2 are in Y. Right? So the opposite corners of this square are the way that you group these. So now notice that every edge in G has one end vertex in X and the other in Y. Okay, so yes, all of these are bipartite. Here's an example of something that's not bipartite. Textbook does this. I could pick whatever here, but I'm just going to repeat the one in the textbook. Here. Can you separate that into 2 sets, X and Y, where the only edges of G have one edge in one of the sets and one edge in the other set? And the answer is no. Nope, you cannot do that. Now, there is a special case of bipartite graph, which is the idea of a complete bipartite graph. So a complete bipartite graph is one whose edge set is of the form If it's a complete bipartite graph, it's already a bipartite graph, so it has partite sets x and y. But its edge set is of the form E, which is the collection of all edges between x and y. So literally every edge that could exist between these does. Right, so that is every possible connection of a vertex in x with a vertex in y is the one that's there, i.e. every possible connection between a vertex in x with a vertex in y. Notice this is not complete. Well, this is generally, this is not going to be complete generally, except in very special cases. So this is not going to be complete for the reason being that the connections between vertices in the same partite set are not present, right, in the edge set. So it's only complete in the sense of it's complete bipartite. So we have seen an example of that. In fact, here's one. But here's another example. Oh, I'm going to redraw that one. Here's another example. So I need to connect every vertex on the left with every vertex on the right. And this is what I was saying you might remember, or you might have done when you were in grade school drawing doodles that did things like this. Okay, we have a way of denoting this. We denote these graphs as K, so we're using the same symbol as we do for complete graphs, but as multi-indices, we have the cardinality of the X partite set and the cardinality of the Y partite set. So this would be K13. This is known as the claw. Okay, you can see why it's known as the claw. This would be K34 because the cardinality of its X set is 3 and the cardinality of its Y set is 4. Of course, you might say, well, what's the difference between K34 and K43? Well, we're coming up on that, so don't worry about it. Okay. Now, bipartite graphs might seem a little bit strange to include in this. Maybe in a sense you get the feeling that the other types of graphs are somehow like a natural thing you would have investigated, but maybe this is somehow a little not as natural, like why this would be important. Well, it turns out that bipartite graphs have very nice properties, or have many very nice properties. One of them I'm going to mention here. I'm not going to include the proof. It's a nice proof, but I'm not going to do it. I'll have you all read that instead. So there's following theorem about bipartite graphs, because it is more important for me to go on and at least introduce the notion of isomorphism before we end lecture today. So a graph with at least two vertices is bipartite if and only if it contains no odd cycles. So if and only if statements, you can view them as exactly when or completely characterizing what it is that's going on here. So if and only if being bipartite exactly means that it contains no odd cycles. Okay. All right. So for the proof, this is on page 14, I believe, of the textbook. You can have a look at it to see where the bipartite nature plays a role here. It's very important. This is not true, of course, for when the graph is not bipartite. So this is very important. Okay, so now the big question, and we'll also start lecture tomorrow talking about this because this is a very important notion. What does it mean for two graphs to be the same? Okay. Well, you might have some intuitive understanding of what you would consider it to mean to if I told you two graphs were the same. Think back to other parts of your math experience. What did it mean for two triangles to be the same? Well, the same was a little restrictive if we went like with the absolute most rigid thing possible. It meant that those two triangles had to be exactly the same triangle. That's a little silly because that means they have to like line up exactly even in space, right? So if I drew a triangle on the page, it would need to the other triangle that it's equal to would need to literally match up to it exactly as it is. But if I draw a triangle over here and another triangle over there, they have the same angle measurements and side length measurements. Even if one is over there and one's over here, so they're clearly not the same. There's two of them on the same piece of paper, right? How could they be the same? Right? We had to come up with another notion. We talked about congruent triangles, which basically meant that one of the triangles could be moved through rigid motions of the plane to line up and be on top of the other one, right? That's what being congruent meant. And that wasn't true if any of the angle measurements didn't the corresponding angle measurements didn't match up. If the corresponding side lengths didn't match up, you couldn't do that, right? So that was what we did. In the notion of, say, you already know where this is going if you've had like group theory or anything like that. But even for linear algebra, right? Vector spaces. What does it mean for two vector spaces to be the same? This was the notion of vector spaces being isomorphic. There needed to exist an isomorphism between them, right? So, well, what did it actually mean, right? You could state me the definition of what an isomorphism is in vector space terminology, but what did it actually mean? Ultimately, it meant that the two vector spaces were essentially relabelings of each other, right? In some sense, that's what it meant. So, for instance, maybe you're talking about R3, right? But you saw that, oh, like three-dimensional Euclidean space is isomorphic to the space of real coefficient quadratic polynomials, right, in the variable t. Like those two things as vector spaces are isomorphic. And you could write down the isomorphism that does it, right? In fact, it sends a vector xyz to the polynomial, x times t squared plus y times t plus z, right? Like that is the isomorphism between those two vector spaces. So Similarly, we're going to define isomorphism between graphs, and it's going to consist of a map, a one-to-one correspondence in some way. But before I do that, I'm going to give some examples. So one, obviously, you have something like this, and maybe this. Are these two graphs the same? And the answer is yes. Yes, they are. You could even tell me exactly the map that's going to get it done, right? In fact, the map choice you make here is not even unique. There are different choices you could make that would make this work. Okay. How about this? I'm going to give you another example. Here's two. Are these two graphs the same? I mean, here's the problem, right? Do they have the same vertex set? Well, no. The vertex set of the one on the left is the set consisting of A, B, C, D, E, F, G, H. The vertex set of the thing on the right is 1, 2, 3, 4, 5, 6, 7, 8. Those are different objects, right, as far as our sets are concerned. Those are two distinct sets. They have the same cardinality. That's important. But they are not the same sets. There is a one-to-one correspondence between those sets. That's important. But the sets themselves are not the same. So we have to be careful, and we have to say something here. The vertex sets are not the same, which means the edge sets cannot possibly be the same, since the edge sets consist of edges labeled by, with reference to the vertices themselves. So, But are these actually the same? And the answer is yes. And you might even be able to see it. Notice that graphs are not so rigid as some other objects you're used to dealing with. You might even see how this is done. Imagine taking this inner square, moving C over here and letting the edges follow it. They're flexible. Moving D over here, I'm stretching the edges. Again, I don't care about stretching. I'm not trying to preserve length here, right? We haven't even talked about length. So stretching something is no problem. That's not good in geometry, right? Like in Euclidean geometry, you're not allowed to stretch a triangle. You're not allowed to dilate or do anything like that. Here, you can't break any of these, of course. You cannot sever these things. You cannot delete vertices. That's going to change things. But you can move C and D here, E and F here. And after smoothing out, adjusting a little bit, the graph you'd be left with is this, except instead of 1, 2, 3, 4, 5, 6, 7, 8, you'd have these these letters going around, right? A, B, D, F, H, G, E, C, A, all the way back to A. These are actually the same, though. Okay? But you're getting your first taste of, even for small graphs, even in a simple case like this, figuring out whether two graphs are actually isomorphic or the same is very hard. It's a hard problem. There's not one quick fix that fixes it all. So what is the definition? Okay, G and H are said to be isomorphic to one another, or to each other. As we'll see, this goes in both directions. If G is isomorphic to H, H is isomorphic to G, because it's a one-to-one correspondence, it's invertible, all those things. So G and H are said to be isomorphic to each other if, or mostly we would just say that they're isomorphic. If there is a one-to-one correspondence, here this means a one-to-one onto map F, taking us from the vertex set of G into the vertex set of H, such that adjacency is preserved for each pair of vertices X and Y in the vertex set of G. XY is in the edge set of G if and only if f of x, f of y is in the edge set of H. I already spilled the beans here on what is actually important, i.e. the mapping F is called the isomorphism. Okay. So F is an isomorphism between G and H. You might notice again that the idea here basically is F is preserving adjacencies. I've run out of time for today's lecture, but we're going to start exactly here for tomorrow's lecture. So I'm going to talk about the notion of isomorphism, what it means, what has to be true if two graphs are isomorphic. You already know this means they are, in some sense, the same graph, and we're actually going to say that, just like we said two isomorphic vector spaces were the same vector space. As far as the graph structure is concerned, two isomorphic graphs are the same graph. So anyway, we are going to start here tomorrow, then we're going to talk about distance and things a little bit after that. So anyway, that is the plan, but that's all for today. So I will see you all tomorrow.